Hi, everybody. Welcome. I'm Faith from Elastic's community team. If you're joining from our Boston user group, hello and welcome again. And if you're joining from our virtual user group, also hello. I'll drop links to the virtual user group in the chat so that folks who are not a part of our virtual user group, you can join there and stay up to date on all of our virtual meetups that are upcoming. So today we're really lucky to have George and Murali from SEMplicity join for a presentation on scaling an ECE deployment. So really grateful to have them, really grateful to have their time today. And they're super knowledgeable, and I'm really looking forward to the presentation. Again, throughout, if you have any questions, please utilize the Q&A feature or the chat. We'll be monitoring that throughout so that we can address anything that comes up. So without further ado, I'll hand over the reins to you, George.
Well, thanks so much, Faith, and thanks so much for giving us this opportunity to talk. We talk at a fair number of conferences, and it's always a good time. This is the first one that's been virtual for me, so I took the I took the precaution of instructing my 15-year-old son to Zoom bomb this meeting if I get into any trouble. So if something happens, you'll know where it came from. So I'm just going to go right into this and not really talk about us. We're Elastic consultants, and we'll talk a little bit about that at the end. There's a technical presentation on how to create a really big Elastic deployment. So it'll have some technical detail in it, but it can't really include everything. So I would also encourage you to contact us directly if we can't get questions answered during this presentation. We're always happy to talk about this stuff. It's very exciting to us. Okay, so let's get right into it then. So what's our challenge? We have a big public company, and this is all based on what we did a while back. We have a big public company that is really struggling to access all their log records. So this is sort of a security use case, but it could easily be a observability use case. Anything that requires an awful lot of data. Log records, really generate a lot of data, and the old way that they were storing them, because nothing's ever a greenfield in this space, the old way they were storing them, it took a really long time for them to retrieve the log records. And they were also chafing under the expense of retrieving all those log records, storing them all. And they were also worried about going forward. The technology they felt was a little bit frozen, and they weren't able to do anything interesting like visualizations or any machine learning or anything with that data. So they brought us in, or we advised them and came in to create a use case for them just to store all their logs, and we called it Fast Search. And it uses Elastic, and it was an interesting application in that it doesn't have that many users. The people that use it are the people who are working in security in the organization. Incident response, SOC analysts, hunt team, forensics, things like that. That's not a huge pile of people, maybe 100 to 200 users. The real challenge was ingestion. It has a very high rate of logs coming in, which we'll talk about. And then, on the roadmap, we wanted to be able to store store logs. Some of these logs are quite sensitive, and they have special storage compliance requirements. And then also on the roadmap, which we've executed a bunch of, is really nice visualizations, all the beautiful stuff Kibana can do for you, and also some alerting and also some anomaly detection with machine learning. We're not going to be talking about the use cases. This is a technical presentation on how to get the logs, a large number of logs, into Elastic, and with a minimum of effort and with the maximum of supportability. So there's our challenge. Here are our metrics. We're talking about just 30 days retention. We'd like to get it up to 60 someday, but they're only interested in the first 30 days of logs in this application for Fast Search. That's because there's that's where most of the action is. If you're looking at security events, you really need to know what's been going on in the previous 30 days, ideally 60. Now, if you're storing events for compliance, you might need a year or 3 years, but that's not the application here. The application here is actually logs that people are going to use and beat on. We ingest, the requirement was about 150,000 events coming in every second. So that makes for 31 and a third terabytes per day. And in terms of performance, we needed our searches over those 30 days to come back in less than 5 seconds, which would be a huge improvement over what they have. Actually, the vast majority of our searches are well sub-second at this stage. Even, this thing's been up for a couple of years now, or for a year anyway. But our SLA was 5 seconds because we wanted to be safe. These are this is the total storage we're talking about. I'm just going to call them 4 data sources, A, B, C, and D. They're all log records from various types of things like firewalls and Windows servers and whatever. Our log A is 117 terabytes, 48, 577, and 202. So we're getting up to a petabyte. It's probably about a petabyte now. These numbers aren't up to the minute. And it's on its way to being expanded to 3 petabytes with any luck. So these are our metrics. This is what we came into this project understanding we had to do. So the first question, let's talk a little bit about Elastic Cloud Enterprise and some of the terminology for it. I won't spend too much time on this stuff. But it's important to understand some of it. So the current terminology is ECE, Elastic Cloud Enterprise, is what Elastic uses itself to run its Elastic Cloud, which is their managed service. Now, this software is also available to clients and MSPs like me, I'm a managed service provider, to license and run on our own hardware if we want to. The client that we were dealing with here really wanted to use 60 servers that they had to repurpose to run ECE on premises. Now, the question is, why would a client want to do that, when there's a nice cloud offering? Well, there's a couple of reasons. In a large, first of all, the servers were just lying around with nothing to do because of another security product that shall remain nameless that they threw out. And they were nice, powerful servers. So they figured, why not use them if they're just lying around in the rack all ready to go? The other reason was that in a large storage deployment, the slight difference, and it's slight non-trivial difference between hosted and on-prem, total cost of ownership, can become really significant. Like if you're only running 3 servers, a cloud-based implementation, the Elastic Cloud might make sense. But if you're a big organization running 100 of these servers, the difference in the total cost of ownership becomes significant. And in this case, the TCO favored running the stuff on site, especially since they got these free servers right at the beginning. So that was what I went around the decision as to whether or not to go with on-prem versus in the cloud. Now, if we're going to go on-prem, we have another decision to make, which is, should we run nodes, individual Elasticsearch nodes, and group them into clusters and manage them ourselves, or should we run ECE, Elastic Cloud Enterprise? And they made the decision to definitely go with ECE because there were just going to be so many nodes, and it's such a big project. ECE centralizes the management of a large numbers of Elasticsearch nodes. So the nodes are containerized in Docker and they're centrally managed. The config stored centrally in Zookeeper, and ECE keeps all your different nodes up and running. And we've got many, many nodes in a big data storage application like this, a petabyte. There's going to be a lot of different nodes running, and ECE manages the whole life cycle of those nodes. And that is worth a lot in a big implementation. Way more than pays for itself. They're all platinum nodes, by the way, under ECE, which is another nice thing. It really facilitates scaling up to deployment because you can easily add capacity with ECE. It's really great. I won't go over all of these, but it's really great with updates and upgrades because you can do a rolling upgrade and upgrade all your Elasticsearch software without any real downtime. It'll just manage the upgrade on its own, which is tremendous. So there's a lot of nice features in it. I have a link in the presentation where you can see, to the definitive documentation. The latest version is 2.5. So we went with ECE deployed on-prem for this client. Here's a reference architecture. So this is a slide from Elastic itself. and it is it's the reference architecture for ECE. I wanted to talk about some of the components. I don't want it to be a big vocabulary lesson, but we have to talk about a few things. So first of all, like the users and the log sources are coming in. Usually there's a nice load balancer. In our case, we used F5s to sit in front of a whole bunch of what ECE calls proxies. These are nodes that distribute the workload coming in from the load balancer. They're purpose-built special nodes designed to distribute. They're intelligent, and they're designed to distribute the requests coming in for both read and write to the most appropriate places for them to go based on load and balance and things like that. That's something that's available with ECE. Next, we've got the workhorse of any ECE deployment are the allocators. These are the things that manage the different containers. So each server is going to, a data server, an allocator server, is going to have an allocator, and it's going to spawn any number of nodes underneath it. So most of these nodes are going to be data nodes that just their general job is to store and retrieve data. A few of them will be a little more specialized. Some of them will be Kibana nodes. In any event, these the allocators are what do that. And then there's also a couple of clusters purpose-built for ECE and management, which we'll talk about later on, that come with this. And then the actual ECE software is up here. These management services, it consists of constructors, and the zookeeper, which manages the config, the director, which distributes the config, and the different administrative and administrative APIs so that you can manage this stuff. These components here are really their own, they run with using an administrative cluster, and that is the heart of this application. ECE is a licensed application, as I understand it. So that means that you buy this from Elastic, and it comes with a subscription, a 1-year subscription. It's based on the amount of RAM that you're running on your servers. So here is our reference architecture. If you need any more, there's the link down there. But this is what, in general, an ECE high-level deployment looks like. And I just wanted to, describe the main components: the allocators, the proxies, and the management, and how they're divided. So let's talk about how we did our work. So in our deployment, we decided to use 3 availability zones because, you don't want 2, you'll get split brain problems. So we did 3, and across these availability zones, we've got 4 clusters. All of this managed by one, ECE deployment. So we've got 4 clusters. Each cluster and each availability zone consists of a master or a master eligible node. That's to control it. That's a small node. That is sort of the traffic cop. We've got those proxies, which we talked about, that distributes the workload. We've got data nodes, which we talked about under the allocators. We've got 2 kinds. We've got hot and warm. Hot is for the stuff that is really getting beaten on hard, and warm is for the stuff that people still need to read. You can also have cold. So that was our architecture. We've got 4 clusters. Each one holds a different kind of log data. And for each of these clusters, we have this configuration in each of the availability zones. So I'll give you a second to digest this, because this is sort of our master architecture. On the right here, we have some other clusters that just come with us. We've got a metrics cluster to store all the metrics that this thing produces, which is super important in a large implementation. We've got a sizing cluster, which is even more important. This is just our sample cluster. When we ingest logs to begin with, we send them to the sizing cluster for a few days, as we'll describe later, to figure out how to tune our deployment so that we get the maximum benefit out of it. And then we've got this ECE management cluster, which we talked about earlier. These are also spread across the 3 zones. So I'll break here for a second if anyone's got any questions about the architecture.
Yeah, in the chat, there's someone who says, can you tell me more about the audited data?
Yes, the log records, the audit D data or the audited data? the two different things, but not really. So,
Sorry. I think I misread that. That was Murali responding to somebody else's question, actually.
oh, okay. Well,
I'm
go ahead, Mirali.
I'm just trying to understand what the audited data she's talking about, Carl is talking about.
Oh, well, I think what they're probably talking about is the data that's going in here, like data A, B, C, and D. And I'll say that these are all security network devices of different flavors. So data A might be, say, the proxies, and data B might be the security logs from Windows. Data C might be all my Linux audit data. Data D might be all my IPS IDS data. These are all sort of network security devices that are generating lots of, they could be DNS servers. We could have routers and switches. We could have anything that's of value to be able to track and detect events in the security organization. A big organization might have 100 or 200 different sources, but the large ones are usually firewall, proxy, Windows and application servers, and of course, especially Windows domain controllers and things like that. So I hope that sort of talks about the data that we're ingesting here, but it could just as easily be performance data. Anything where you have a lot of data, this architecture is applicable. And with this data, we siloized it by the type that it was, so that all the IPS data is in this silo here. But as we'll talk about later on, we can search across the silos if we need to. Alrighty, I hope that answered the question. So let's drill down then and take a look at what the architecture looks like in a particular cluster. Like previously, we saw high level what it looks like, but let's look at what a particular cluster looks like. So say here is what all our clusters look like in one form or another. As I said, each cluster is dedicated to a particular type of security data, Windows logs, firewall logs, whatever. So we'll start from the bottom here. All this stuff's getting written to Kafka, which is a great thing. It's a great way to deliver data because it's if something goes down, it just stores it up and then sends it when it's ready. It's also pretty high performance. So all of our stuff is getting delivered to our cluster of LogStash servers, which we'll talk about in a minute. And these LogStash servers enrich the data and they send it to a load balancer, which is not an Elastic component, it's just an F5. Similarly, users are logging on through their web to Kibana, through their browsers, and going in through the load balancer, and the load balancer distributes it among the 3 availability zones that we have. So that way, if one zone goes down or something goes wrong, the other 2 will keep running. The availability, now the proxies then distribute it to a whole bunch of, using the masters in each zone, it distributes it to all the different data and ingest nodes, and there's many of these. So in this 1, 2, 3rd silo here, the A zone 1, 2, and 3, there are many data and ingest nodes in each one. So, and the data is spread across all the 3 availability zones so that if something happens, we won't lose anything. And that's, of course, the great power of Elastic, is that we can run in replicated mode, so we don't need to use RAID 5 or things like that. We let the software replicate for us and assure our reliability and redundancy. So within each availability zone, we have the hot and the warm servers, right? So the hot ones are red and the warm ones are, more gray here. And we have lifecycle management that takes after so many days, it moves from hot to warm and then, to cold. And so this is what any one of those particular, if we want to go back one, any one of these particular silos, this is what it looks like in detail. We've got proxies, a master, and we've got data and ingest nodes. Everything goes to our monitoring deployment here. So that we can keep track of everything that's going on. We built that in from the beginning because you really do need that in a big deployment like this. So let's talk about then our challenges. with this deployment and what happened and what went wrong and what went right. So the biggest problem we had is that we inherited this hardware, right? So we didn't really control it. And it was 60 plus Red Hat servers. And so the problem was it was heterogeneous. Some had like small SSD drives, some only had spinning disks, some had a little of both. They had different amounts of storage. They fortunately all had the same amount of RAM, but they were, very different. Each one had different performance profiles, or each group of them. And then to add on to that problem, as the deployment got bigger, we added 12 servers with a lot of SSD for hot storage, and we also managed to fit 11 hyperconverged virtual servers. Those are sort of virtualized storage and virtualized OS. For the lower volume storage. So we added a bunch of servers in the middle. All these servers have very different performance profiles. All of them have different amounts of disk. They have the same sort of amount of memory, but a virtualized server is very hard to hyperconverged server is very hard to dig into what it's actually getting. So because of that, it forced a number of difficult trade-offs, and it complicated our architecture. And we had to do a lot of analysis. In a perfect world, if you were starting from scratch, our advice would be to have like 4 server profiles, really, just 3 that are important. A profile for the hot servers that has a lot of SSD storage. A profile for the warm servers, that would be about 50% of your capacity, that have spinning disk and denser storage, and then maybe 40% for some colder frozen servers that have spinning disks, say 5K disks with extremely dense storage. And then don't forget, we'll need some VMs for LogStash that have a lot of CPU and RAM, because we'll talk about LogStash here in a minute. So in a perfect world, if you're starting from scratch, you'd want to have a template. And you'd probably have 3 server templates, one for hot, one for warm, and one for cold. And you just stamp out these templates with however many, whatever your requirements were, and they would all be the same. And as we'll see, that would really facilitate the tuning, as we'll see in a few minutes. So if we're done with that, let's talk about the first issue, which is the master stat with this sort of stuff is the storage density, which determines how much disk storage you can have per gigabyte of RAM. And that is sort of if there's a master switch in Elastic, that's the one. So what we did was, it was pretty straightforward. We have 256 gigabytes of RAM, 24 terabytes of storage. So we figured we'd be somewhere around 1 to 98 for each allocator. We could make that less and be less dense and waste some storage, but also have better performance. This was a trade-off. We decided that we were well within our performance parameters, so we went with a 1 to 98 storage density. So this is from the ECE panel here. Sort of, you can determine how much RAM per instance ECE you're going to run. So let me see if I can explain this. We found that each ECE instance, which is like an allocator that is going to, underneath it, it's going to create the Docker containers that run Elasticsearch, that run the Elasticsearch shards. So you can have bigger containers or smaller allocators. We found that for our application, 64 gigabytes it was an optimal size for our instances, our allocator instances. Underneath that, we could create the necessary Docker containers to do what we needed to do for each one. When you allocate the RAM, it also allocates the processors on the machine. So if you allocate 64 gigabytes of RAM, you get 16 processors. With 16 gigabytes, you only get 4. So, you might be tempted to run smaller instances that are more single purpose, but you suffer a little bit in terms of the CPU for that. So you want to, you have to calculate your storage density with the size of the instance in mind. So this is the other tuning parameter. How big do the instances have to be? So let's go through a little bit of an exercise. So let's say we have a server that we plan to use like primarily as a data, to run data nodes with 24 terabytes of storage and 256 gigabytes of RAM. Well, after we install ECE, that takes up some room of RAM, so we really only have 213 of RAM available for our nodes. If we run with a 1 to 93 RAM to storage ratio, we can get 5.9 terabytes per node. That means we can run 3 64 gigabyte nodes plus per server. And then there's some room left over to run smaller nodes, like the Kibana nodes don't require anywhere near that much resource, and the master nodes are also very small. So we can run 3 of them at 64, which is which gets us up to 192, and then to the remaining 213, we can take up with some of with like the Kibana nodes or things like that. Now, this is the problem with this is that, and this is where the standardized sizes come in. And I hope I'm not. I hope people are following. If not, well, we won't spend too much time on it. Without rounding, like if we didn't round up from 1 to 93, it's 1 to 93.75 gigabyte of RAM. So if we round down from 1 to 93, that actually means for each server, we're going to lose 192 gigabytes of just disk storage that we're not using at all. And so we lose that as well. So then, because of that, also, it's compounded because we can only fit so many 64 gigabyte nodes, right? We can't fit 4, we can only fit 3 on this one because we only really have 213 gigabytes of RAM available. So because of that, it's not a big deal, but we get, out of 24 terabytes available, we get 23.8, which I guess means we've got 200 gigabytes of lost storage. It's not a big problem on this particular one, but it gets really hard to manage when all your servers are different. So you could see how, like, if you had one server and one template, you could size this up and you'd be in business. But there's a whole bunch of servers. It's difficult to create templates such that you don't avoid wasting space. And I won't go into too much more detail on that, but I'll break for a second if anyone's got any questions. Alrighty. So let's talk. The next thing is about sizing the shards, and this is an exercise that you go through when you have to put together a big deployment. Very important is to set up a monitoring deployment where you can turn the fire hose on and see what happens. Because then you can make your determinations. So what you have to do is figure out, first of all, how many gigabytes for this particular cluster am I going to ingest per day? So if we figure 1,300 gigabytes, we're going to do a replica, so now there's 2,600 gigabytes. We want to oversize it by 25% because these things are always growing. Then we multiply that times 30 to get 97 terabytes. Now we have to determine the size for the shards. You don't want, the idea is to, we experiment with different shard sizes. We think 60 or 50 is probably where you want to be on a shard size. The rule of thumb is not to go over 60, or at least it used to be. So if we figure out 60 gigabytes per shard, that means we have to run with 54 shards. And that's how you calculate when it asks you in ECE how many shards you want. That's how you calculate it. So for this cluster, 54 shards are going to be spread out. So that's shard sizing. So now the last thing we have to do is size the nodes, right? So we went with 64 gigabytes of RAM per data node. I'm talking about a data node here. The Kibana nodes, the master nodes are much, much smaller. But mainly you're running data nodes. So if we go with a node size of 64 gigabytes per 6.1 for your storage, that's a density of 1 to 98. Then we have to figure out how many we can fit per server. And this is just running through the calculation. We figure we figured we would need 16 nodes. We have 3 zones, that's 16 servers, right? We have 3 zones. So, because we want it to be divisible by 3, we figured 18, we'll put 6 in each availability zone. So for this particular cluster, we would do, we have to store 97 terabytes in 30 days. We'll run this across 18 different nodes or Elasticsearch instances running across the 3 availability zones. That's 64 bits, and that's how we did it. So I don't know if anyone has any questions here, but I'll keep going unless interrupted. So a couple of things to think about shard sizing, and people might disagree with me on this, but we found that you can size the shards however you like. If there's smaller shards, we found that it takes longer to write, but faster to search. That means there's smaller shards, but there's more of them, right? So if you have more shards, but they're each smaller, you do get faster search response, we found, but it does take longer to write. This is just our experience. It's a complicated issue. If we have larger shards, but less of them, it has the exact opposite effect. It ingests faster, but is a bit slower searching. We sort of prefer the larger shards as things go because our application struggles with ingest, not with search. We don't have that many users. The search stuff comes back nice and fast. But the trade-off with that is that it takes longer for Elasticsearch to relocate the shards and for ECE to move them around and also to perform upgrades. If the shard's bigger, it takes longer to move it somewhere. But that's a trade-off. These are general guidelines. The best way to do this is to set up a sizing cluster and then point your event source at it first and tune it until you get the performance you want. Because it really is, as you can see, if you take nothing else out of this, it's that the performance here is dependent. There are different levers that we can use to control the performance. We can control the shard size, we can control the node size, we can control the storage density, which is super important. How we tune those things depends a lot on the hardware you're running on. And it depends a lot on the EPS that's coming in. So the best way is to have a sizing case, a sizing cluster, where you can just do your own tuning for your particular log source and or data source and for your particular hardware. So next up, let's talk about everyone's favorite subject, LogStash. We didn't think we'd have a lot of work to do with LogStash, but actually there was a fair amount of work to get it to ingest at this rate. As I've anticipated in this presentation, some of our problems really centered around ingestion and getting the Elasticsearch deployment as a whole to ingest these log records at the appropriate rate. And that is a function of both Elasticsearch and of LogStash. So we'll talk a bit about LogStash tuning here. First of all, the data we were dealing with has already been parsed, so LogStash didn't have to do that much work to parse it. And fortunately, the data was already in Kafka, so we could just pull it right out of Kafka. It's really easy to do. You just subscribe to the topic within LogStash and it reads it. The real issues were how many instances of LogStash do we run to be able to handle our EPS? So let's talk in some detail about that. We initially decided that we would have, we take 2 of our, lamer servers and use them for LogStash. And each of those servers would run a number of LogStash instances, 3 to 5, and that these things would each read Kafka topics and write to Elasticsearch through the load balancer. Later on, we added 10 more VMs configured especially for LogStash, and each of those servers runs several LogStash instances. Now, it's important to remember that LogStash doesn't run under ECE at this point. You could deploy it as a Docker container, but we didn't do that. We just ran separate instances of it on these servers, probably because we were lazy. We do send all our LogStash metrics to our monitoring cluster because it really helps with tuning. Here's what LogStash configuration would look like to collect events from Kafka. It's really pretty straightforward if you know the name of the doctor of the name of the topic. So when pulling data, the number of Kafka partitions is important. You can only have the number of threads as there are partitions that you're trying to pull from. And in our case, our topics had 60 partitions. So LogStash can only have 60 consumer threads per instance. And so that's important to realize, because you think you're going to speed up LogStash by giving it 200 consumer threads. It's not going to help, because it can only handle one thread per partition. So what the answer is, another more LogStash instances. Right? That's the answer to that problem. So here's what it looks like applied. If we've got a high volume cluster with maybe 50K EPS or 40, we'll split it among 4 LogStash instances, each running 15 consumer threads, for a total of 60. The guidelines are the general guidelines for ingestion are there. Lower EPS, you need fewer instances with a high number of consumer threads. With high EPS, which is what we're talking about here, you need more LogStash instances with a lower number of consumer threads each. But in either case, it's all going to add up to 60. And also the JVM has some effect on that. So the bottom line is down here. If you just run LogStash out of the box, we found that we could get about 2,000 EPS ingested by it. If you set up if you tune your consumer threads and everything like that, we can get a single LogStash instance up to about 5,000 EPS. But that still means if I've got 30,000 EPS, that means I need 6 LogStash instances feeding that cluster. And that is just the way LogStash works. Fortunately, you can run them in VMs. They don't require that much disk space, but they do require a lot of CPU. So that's sizing LogStash. In terms of tuning LogStash, the highlights are the all content keyword. You can run faster or slower depending on your mappings and the different things you do in LogStash. And it really makes a big difference. So one thing is the all content, which is just your free-form text field. We concatenate a lot of stuff into all content. Anything that because the people who use our application might not know the label of the thing they're looking for. They might just be looking for George. They don't know whether or not it's in the user name or the user ID or somewhere else. They just want to look for it everywhere. So they can do that if it's indexed in this all content field. So we had to do a lot of that, which does slow things down a bit. On the other hand, you can speed things up by not indexing fields that really are not going to be searched, like numeric fields, right? If you've got an integer field that ranges from like 1 to 200, no one's going to do like there's no need to index it. That speeds up the ingestion. This topic, we're getting near the end here. This topic is dear to my heart. One thing that slows down LogStash but is super useful, is enriching the events. LogStash, you could do this in Kafka too. LogStash is really good at enriching events that are coming in with data from outside, from different sources. So right now we get GeoIP data, which comes by default out of the MaxMind database, and we're working on using the MaxMind commercial database instead of just the freeware one, because we have subscriptions. And we also, and this is super useful in a big organization, is we're grabbing the information on the servers from IPAM and the network segments and the different subnets, and all that stuff is really valuable. And so we're enriching the events. Any IP address, we also can tell you exactly where it's coming from in the organization. Which site is it coming from? Which office? Which server? Where is that server? Is it a PCI server? Is it some super sensitive server? Is it something that's not important? Which, whereabouts is, which site is it coming from? Is it coming from the Milwaukee office or the Chicago office, or even which room it's coming from? All that stuff is, organizations maintain this in an IPAM database in general, and we can use that to enrich these events as they come in, and we do that, and it doesn't really affect performance very much. It's tremendous. Murali figured that out. He used we created our own MaxMindDB. And instead of populating it with GeoIP information, we populated it with network information from the internal network and used a LogStash MaxMind filter. That's the best way to do it. If you, it's tempting to store the stuff in Elastic and then read it as the LogStash, as the stuff comes into LogStash, but that we couldn't handle that with the EPS we have. We're working on enrichment now with threat intelligence from MISP and vulnerability from vulnerability management systems and identity data as well. Eventually, I would like a bunch of all our events to contain this. So if it's from a known bad IP address, we'll know that, and we'll know exactly what kind of IP address this is. Is it like a click fraud, or is it a phishing one? If we would also know the vulnerability of any specific devices, which really helps people. And we'll also know if it contains a user ID, who that user is, like what's their role in the organization? Are they like the CFO and they've answered a phishing email, which is sort of a big deal, or is it just someone like me who's did something stupid, but no one cares? So that is, all this enrichment enables the advanced use cases like machine learning, and it also really helps our analysts who are good looking at the events. So let's talk about the main problems we saw in this, other than trying the sizing and such. The big problem that you see here in a high volume thing is ingestion delays. You don't lose any data, but the data that shows up is an hour late. And the reason for that is we found the biggest problem. We still have these problems, and the solution now is to add a LogStash instance. But before, regardless of LogStash, we were seeing this. And what happens is that ECE keeps all its shards equally distributed. So what we found was that if you add a new node, like a new server to your deployment, ECE was routing all the new records were being written to that one instance. So one server was carrying all the load because it was brand new and it didn't have any, it had loads of capacity. So all the shards are being created on one instance, and it will keep doing that until everything's balanced, but that really slows stuff down. Obviously, you want your ingestion to be spread across as many instances as possible. So, what you see is that, we want our information to become available within a minute of showing up, but we were seeing stuff that was hours late. That's no good. So the solution is just to set this one parameter here. You just set a routing allocation to all, and that is done right here. There's the URL to do it. If it's set to something else, you can just set it to null, and that will reset it to all. That was important, and that was a tough lesson learned. The other lesson learned was that when you're first starting this thing up, if you have problems with your configuration, it will erase the error messages in the Docker containers sometimes before you've had a chance to actually look at them, which makes it really hard to debug. So there's a deployment strategy, it's a parameter in ECE. If you configure it to rolling, then you won't actually immediately delete that log or container, and you can go look at the log file and see what stupid syntax error you made instead of just going crazy. So that was one problem that we fixed. This is just so you know, since ECE 2.2, we can do cross-cluster searching across all our different clusters, which is necessary in some cases. So the data is not siloized. It took some doing on Elastic's part because originally ECE was designed to actually prevent that from ever happening for multi-tenanted stuff, but it is quite possible now, and it works great, and we have our own cross-cluster search set up. It requires its own, well, in our case, we set up another cluster that is really just, it's a small cluster that talks to all the other clusters, so you can run a search across everything and sort of say, show me every log record that George has shown up in across all my data sources. So here, we're getting near the end here, our general tuning guidelines. You have, before you start, you really have to know your EPS. And if you're doing replicas, it's going to be like double. The master tuning parameters, the RAM to disk ratio, identical hardware makes your life easier. What mistake that we made was we really didn't put aside enough hardware for our LogStash. Really, the best that we've been able to do is 5,000 EPS per LogStash instance. So if you've got 100,000 EPS, you're going to need 20 of these LogStash instances. They all don't have to run on separate servers. They can run on, five. You can run 3 or 4 of them on the same one. But at a certain point, you're going to need to do that because we didn't plan for that, but we figured it out. And then, the indexing options, you really need to take a look at the defaults. You can reduce the number of keywords mapped. You don't need to index every field. There's many, nice tuning possibilities on that. So you have to know your use case to be able to do that. But anything you do there really, it speeds things up and it reduces the amount of terabytes you're using up. Alrighty, so let me put this sort of stuff in context for a second, and then we'll be done. So we specialize in the security use case, though we're doing some observability stuff. We perceive security as a pyramid, and we have spent all day here on the bottom layer, which is log and the bottom 2 layers: log transport, parsing, enrichment, and high availability ingestion. Our view is that anything else you want to do in the security realm is built upon that. Unless you can actually ingest these logs and search them and have them come back really fast and have them be safe and redundant so that you don't lose any data, unless you can parse them, unless you can enrich them, then all these other higher level use cases that everyone's talking about are just not going to work. It's because it's garbage in, garbage out. Once you have really solid Elasticsearch foundation, we've been able to build all kinds of exciting stuff that, the really interesting and fun stuff on top of it. All the visualizations, the alerting, to be able to correlate different alerts together, different events together, and tell people about them. All really beautiful visualizations for the executives. They can look at that and say, oh, that looks like we're doing something useful. And also anomaly detection and machine learning. That's all really useful if you parse your logs. You could really see, like, obviously, say, for a simple use case, user behavioral analytics, you have to know who the user is. The log record has to be enriched with that user's identity so I can correlate it across all the different log sources. Once I have that, now I can really show that, hey, George is doing something that he never does. Somebody needs to give that guy a call. So that is our holistic view of where this stuff fits in. It's here on the bottom 2 layers, but it's super important because you can't really do any of this higher level stuff unless you have those bottom layers sorted out. In terms of us, we are consultants. In the security space, we have been since 2009, particularly focused around event detection and log management. We have an MSP that provides Elastic as a service. We have been pretty, for most of our history, we've been focused on the very large enterprise space. But, now that we're in the managed service business, we're getting a lot of interest from the small, medium enterprise and even medium-sized business space, and we will help people out with that as well. We'll do on-prem or we'll do Elastic Cloud, but in any event, we'll help get this stuff up and running for you and run it for you and manage it for you. That's what we're up to. So I hope this was somewhat useful. Does anyone have any questions? Or I didn't have to Zoom bomb the meeting, so I suppose that's positive.
So there's a question, how do you manage / control shard migration during deployment process? If the shards are big or if there are too many shards in big clusters, such as yours, do you run into problems with long deployment cycles?
Well, I believe the answer to that is yes, but Morale has more direct experience of that. We always do rolling deployments. I know that much. But Morale, do you want to speak to that? You might be muted. Can we unmute him? No, I can't. Oops. I think you're muted, Morale.
I unmuted him.
Okay.
So the question is about how do you manage or control shard migration during the deployment process of the shards of recovery.
Right.
Yes, if the shards are large, we do run into problems. It just takes long time to migrate them to newer allocator. But if you are doing a rolling upgrade, then there is no need for the shards to migrate. It'll just come up upon the successful upgrade of that Elastic instance. But the problem we come up is when the allocator is unhealthy, and if you have to move that node, if you have to move the contents to another allocator, then that's where we run into problems. There is no, I don't believe we can control, I've not found a way to control the migration process or the move process, but it just has to go through the migration from an older unhealthy node to a newer node.
Yeah.
I hope that answered your question, Rahul. Okay, he says yes.
Yeah, I think it makes sense. But the rolling migration does help. I know that did help us out a lot. It's just when something gets sick, it can take a long time to move that shard around.
Yes, the rolling upgrade. So here is a scenario. We have 20 allocators running, and all of them are fully utilized, or all instances have been allocated on those allocators. So in order for you to do an upgrade, the only option you have left with is the rolling upgrade. You do not have capacity to do a rolling grow and shrink, where it will do an upgrade one instance at a time, or you do not have enough capacity to do grow and shrink because you do not have enough capacity to bring up 20 new instances. The only option you are left with is the rolling upgrade that does what you want the system to come up with. If you want the system to come up with a new version of Elastic, that's the one option you have to do a rolling upgrade,
right,
or rolling change that will not move the shards from that specific node to a newer node to another node.
That makes sense. Cool. Well, that's really helpful. Do we have any other questions out there, Faith?
I don't see any so far.
Okay. Well, we love to talk about this stuff. So if anyone wants to contact us directly, feel free to just send an email and we'll schedule a call. But if you've got a particular question on how this stuff works, or you get stuck with something, we haven't seen everything, but we've seen a lot. So just give us a call. We'd be happy to help you out, or send us an email. But thanks a lot today for everyone's attention. I hope it proved useful, and I mean it's a special use case in the sense that it's a lot of data, but I think that Elastic's going that way. I mean, in general, everyone's going to have a lot of data eventually. And it's perfectly manageable to do it, even at sizes much larger than this. and hopefully with presentations like this, we can show people some of the trade-offs and how to do it.
Awesome. Thank you so much, George, for your time. Really appreciate it.
Thank you, Faith. This is very enjoyable.
It says, so there's a question about where the slides and video will be posted. So if you registered, whichever page you registered through, you will see both the slides and the video on that page in the next few days.